Welcome back to Wood Engineering. My name is Jeff Verochko from Carleton University, and today in this video I'm going to look at how to calculate compression resistance at an angle to grain. So far we have looked at how do I find the compression resistance of a piece of wood where the load is applied in the same direction parallel to the grain of the piece of wood. Separately, we've looked at how do I find the resistance of a piece of wood with the load at a direction that is perpendicular to the grain. So if this is the grain, if I apply this way, or if I apply this way, the load, I have a bearing strength that I need to calculate. But what happens if I have neither of those pure cases and I have something that is somewhat in between? So I'm applying the load in compression at some angle to the grain, not aligned or perpendicular, but at some angle. And in order to do that, I'm going to have to apply some kind of interaction equation between the two to figure out what would be a good effective strength to calculate that takes into account both the resistance parallel and perpendicular to grain. So to do this, we are going to look at a example geometry. Okay, so here I have two pieces of wood, one piece framing into the other, and the idea is that I have this piece of wood that is diagonal, that is applying a load that is aligned with its orientation, grain direction, but is not aligned with the piece that's receiving it. Okay, so there's some notch cut in the bottom piece to receive the top piece, but the load on the bottom piece is at some angle to its own grain. So I've drawn kind of grain markings so that you can kind of remember what the grain directions are. But, you know, for example, for this piece of wood, the grain goes this way, right? And for this piece of wood, the grain goes in this direction. So to calculate the top piece of wood, the bearing resistance at this bearing interface, this is the bearing interface we're talking about here. To calculate the bearing strength for the top piece of wood, we just use the strength that we're just going to use the compression parallel strength that we're used to. So that bit's easy. But how do I calculate the strength of the bottom piece of wood? Because that load, which I am going to call NF, is at an angle to its grain direction, right? So its grain direction is this, and the load is coming like this. Okay, so it's coming in at some angle relative to the grain of theta, okay? And this is the key angle here that is going to come into the equation that we're going to look at later. It's the angle between the grain direction and the loading direction. Okay. So how do I do this? Basically what I'm going to do is I'm going to find two different strengths. I'm going to find the strength of the bottom piece of wood parallel to grain, and I'm going to find the strength of the bottom piece of wood perpendicular to grain. And I'm going to use two projected areas to calculate those strengths. So basically what I'm going to do is I'm going to split this bearing surface that's on an angle, which is in brown. Let me draw that. Maybe I'm going to draw purple. So purple is the angled grain bearing, the angled bearing surface. I'm going to split that bearing surface into some component that is parallel to grain, perpendicular to grain, and one component that is parallel to grain. So I'm going to, so this is a component that is the perpendicular to grain component, or sorry, the parallel to grain component, and this side will be the area that's the perpendicular to grain component. So I've split this into two different bearing surfaces. Okay. And this bearing surface down here, this is going to be my QR. Find QR for this area. And this bearing surface over here, I mean, I'm drawing the length. It obviously also has a width, which is equal to the depth of the bearing surface right here, which might be the depth of the member. This one is find PR for this area. Okay. But, you know, obviously we're going to assume that since we're just doing a local, we're basically trying to calculate the local crushing strength here, we're not going to take into account buckling for the bearing strength of this piece of wood. So we're going to consider that Kc, which is the slenderness factor, equals 1.0, which is tantamount to assuming that there's no buckling. Okay, so this is like I've taken my NF and I've split my NF into two components, one component that is perpendicular to grain and one component that is parallel to grain. But I'm not going to compare those individual components to the individual resistances. What I'm going to do is, instead of taking this approach, I'm going to take my total NF and I'm going to compare it against a resistance. So really what I'm doing is I'm calculating one resistance here and one resistance here, and I am combining the geometry of those two to come up with an effective resistance. And it's not just combining the vectors. There is an interaction based on material mechanics instead. So I can't just combine those vectors together and figure out like a total strength. It's actually going to be somewhere in between those two strengths, right? If I combine the vectors together, I would get a longer vector. But that's not the way that it works. Okay, so I find those resistances QR and PR, and then I plug them into a resistance interaction equation. And it looks like this. It's going to say NR. N is just like a force at a general angle. So this is a resistance at some angle. And it's going to equal PR times QR divided by PR sine squared theta plus QR cos squared theta. And once I plug those two values in, and where theta is the angle between the grain direction and the load direction, then I get a resistance NR that I can compare to my load NF. And that's basically all there is to it. So we already know how to calculate PR and QR. So all we have to do at the end is we just have to make sure that we're using the correct areas, which are the pieces here shown in blue. And I'm going to use those correct areas to calculate PR and QR, put them into the interaction equation, and then I'm done. So next we're going to do an example to show how this works.